friends. As you are aware, in previous session we discussed discrete probability distribution, wherein we have seen binomial distribution, Poisson distribution, hypergeometric distribution, and we have all seen continuous distribution as well, and the distribution which we have looked at was uniform continuous distribution. Today we will see one more continuous distribution, which is normal distribution. Out of all the distributions available, I would say that this is the most important one. It has got larger applicability compared to other distributions, and it is a distribution which is applicable in variety of situations. So, as we know that normal distribution is most important distribution for describing continuous random variable, right. In discrete distribution, we have seen that a discrete a random variable was taking a discrete value, right. It is widely used in statistical inferences. So, as I have already said, it is most widely known and used distribution. It fits several human characteristics, be it height, be it weight, be it income, be it length, be it intelligent quotient or scholastic achievement, years of life expectancy, and there are many more. So, you take any human characteristics, this binomial, this normal distribution will fit that particular characteristics. And this is not only true in just one country or one region, it is applicable across the world. And if you want to, let us say, apply normal distribution height of let us say height of Indians, and if you want to know whether that height will follow normal distribution or not, yes, it will follow. If you take height of all the people in the world, then will it follow normal distribution? Yes, it will follow, right. So, it is applicable everywhere. It is not only applicable to human characteristics, but to the characteristics of living things as well, be it life of tree or let us say life of insects or animals. So, this normal distribution, it exhibits characteristics of living things as well. Apart from human characteristics and living things characteristics, many variables related to business and industry are also normally distributed. Again, let us say the income of companies, and let us say the life of companies. So, all these will fit normal distribution. Apart from this, let us say the insurance premium, let us say the cost per square footage of renting warehouse space, manager satisfaction with support from ownership on a 5-point Likert scale. So, all these variables and other variables related to industry will also fit in normal distribution. It has got wide variety of applications. We have already talked about heights of people. So, we will know that within 2 sigma limits approximately 95% population will fall, right, or the height of the population will be 95% within 2 sigma limit. Similarly, scientific measurements, test scores, let us say there are 12 lakh students taking one particular examination, and if you compare their marks, once you have got the marks of all those students, then you will find that their marks would also be normally distributed. Whether, and if you do it, let us say for female students and for male students, then also you will see that the marks of female students would be normally distributed, and again for male students as well. Amounts of rainfall again normally distributed, be it in a country, be it in a district, be any region or worldwide. So, you will find that the amounts of rainfall is also normally distributed. Let us look at normal probability density function similar to other density functions which we have seen. So, we will have density function, mean and variance for normal probability distribution as well. So, normal probability density function f x is equal to 1 upon sigma under root of 2 pi e to the power minus into bracket x minus mu whole square divided by 2 sigma square. So, here mu is mean, sigma is standard deviation, pi is 3.14 and E is 2.71. Now, if you look at this term carefully, so this is E x minus mu whole square, this 2 sigma square, right. This is nothing but a z score also. This is, you can write it like this, 1 by 2 x minus mu sigma square, right. In other words, this is z square, isn't it? This is the formula for z. Z is equal to x minus mu divided by sigma. So, we will see this expression little later. So, normal probability density function is given by this equation. Now, let us work out couple of examples, and there are some more characteristics of normal probability distribution. The distribution is symmetric, its skewness measure is 0. So, if you look at this, its measure is 0. So, this is a symmetric curve, it is not a skewed curve, right. So, area in this region is 50% or 0.5, in this region is also 0.5. So, area under this curve is unity, right, 1, right. So, it is a symmetric distribution, one of the characteristics of normal probability distributions. So, it is symmetric, right, but this distribution, this curve never touches this axis. Okay. The entire family of normal probability distribution is defined by its mean and standard deviation. So, this is a distribution, a normal distribution, and if you want to define normal distribution, then it should always be defined in terms of mu and standard deviation, right. So, this is how you can define a standard distribution curve, right. The highest point on the normal curve is at the mean, which is also median and mode. This another characteristics of normal distribution. So, this is the highest point, and it would be, so mean, mode and median all will be same, and that is the that is one of the properties of normal distribution. The mean can be any numerical value, it can be negative, 0 or positive. So, let us say this distribution, right, this distribution, this mean is 0, isn't it. So, all the values towards right to 0 would be positive, and values towards left hand side would be negative. So, for this particular distribution, mean is 0, right. Now, if you change the distribution from here to here, right, then its mean is now negative, minus 10, right. Similarly, if you shift it in this direction, so this is now mean is 20. Okay. So, it can have mean 0, positive or negative, right, but its variance can never be negative, because you calculate variance by just squaring standard deviation, right. The standard deviation determines the width of the curve. Larger values result in wider, flatter curves. So, this is standard deviation 15 for, let us say this is curve A, this curve B. So, for curve B, standard deviation is higher than curve A. So, it will always be wider curve and a flatter curve, right. Let us draw one more curve, curve C, right, and whose standard deviation is, let us say 30. So, how that curve would look like? So, that would be like this, is not it? If AC is, let us say 10, how that curve would look like? That would be like this. Is not it? So, this is, let us say curve D and having standard deviation 10, right. So, this is how you can have a curve related to its standard deviation. And when I say this S, here I am talking about standard deviation of the sample. The probabilities for the normal random variable are given by areas under the curve. The total area under curve is 1, we have already seen that, right. So, this entire area is 1, right. Some more characteristics. You will always have 68.26 percentage of values within 1 sigma limit. So, let us look at this curve. This is your mean, this 1 sigma limit, this minus 1, this is plus 1, right. So, minus 1 plus 1, this minus 2 sigma, minus 2 sigma. So, within 1 sigma limit you will have this much area, 68.26. It means one side how much it would be? It would be 34.13, is not it? So, within 1 sigma limit 68.26 percentage of the area, within 2 sigma limits 95.45. So, let me, this area, this total area, this area is nothing but 95.44. Now, this is minus 3 sigma, this and this is minus 3 sigma. Now, this area is, this area would be 99.72, right. So, this is again one of the important characteristics of normal distribution. Right, within 1 sigma limits, 2 sigma limits and 3 sigma limits. Now, look at what is standardized normal distribution. So, if you look at if you are given, let us say mu and sigma, then you will have a distribution. For a different value of mu and sigma, you will have another distribution. So, for every pair of mu and sigma, you will have a different normal distribution. For let us say first case where mean is 50, standard deviation is 5, right. This is 5, is not it. So, this is first case. For second case, mean is 80. So, this mean is 80, is not it, and sigma is 5. So, this is case number 2, right, point number 2. And third one is mean is 50, yes, the same one, and standard deviation is 10. So, just see in this case first and third the means are same, but standard deviations are different. So, standard deviation is 10 in case of third, that is why you have got a flatter curve, right, is not it. Now, we know that for every parameter you will have a normal distribution. For every set of mean and standard deviation you will have a different normal distribution. Now, these characteristics of normal curve would make the analysis very tedious, because you will have to prepare volumes of normal curve tables for each set of mean and standard deviation. So, if you want to, let us say, prepare normal curve tables or Z tables, then you will have to have lots of tables for each pair of mean and standard deviation. So, this problem can be overcome by using something called Z distribution or standardized normal distribution. So, a mechanism was developed by which all normal distributions can be converted into single distribution. So, if you got, let us say, hundreds of pairs of mu and standard deviation, then you can convert all of them into Z value or standardized normal distribution. So, the conversion formula for this is this, it is given here. So, this is Z is equal to x minus mu divided by sigma, right. So, a random variable having standardized normal distribution will always have mean is equal to 0 and sigma is equal to 1. Okay. So, you can represent any given distribution either in terms of its value, let us call it x, and it can easily be converted into z. So, this is now z scale, right, rather than having x scale. So, you can convert x scale into z scale and vice versa. So, this how you can convert x value into, you can easily calculate z value by using x minus mu divided by sigma. So, we can think of z as a measure of number of standard deviation x is away from mean. This is what we have calculated when we did find out outliers. We have seen two methods for calculating outliers. The first one was IQR and the second one was z value. So, this is the same z value. Now, let us look at a couple of examples. If x is distributed normally with mean of 100, so mean is, so let us look at mean value 100 and z value as, okay, which we will calculate, and standard deviation is equal to 50, right. Now, what would be the z value when x is 200? So, if x is distributed normally with mean 100 and standard deviation 50, the z value for x would be what? So, you can easily calculate, we know that is x minus mu divided by z, sorry, sigma, this z. So, x is 200 minus mean is 100, this is 50. So, this becomes 2, right. This is how you can calculate z value. Now, this says that x is equal to 200 is 2 standard deviation above the mean. Above the means towards right side or left side. So, this is mean is 100, standard deviation is 50 and this is z value. Let us say this is 100, this is 200, z is equal to, if you convert, if you have z scale, so this is 0 and this is 2, right. So, we will say that this x is equal to 200 is 2 standard deviation towards right side of the 0 value, right, and this is your. So, you have got 2 scales over here, this is your z scale and this is your original variable. So, as we have already said, and we have always said that the mean is equal to 0 and sigma is equal to 1 for standardized normal distribution. So, the shape of the distribution is same, only what has changed? The scale has changed from the original x unit to standardized units, right, which is z. So, this is how you can convert x value into z value. The cumulative standardized normal table gives probability less than desired value of z. So, you can have a z value from negative to some positive value. Let us look at the area under curve when z is equal to 2, right. We are solving the same example where mean was 100, standard deviation was 50 and x was 200, right. So, what is the probability or what is the area under the curve when z is less than or equal to 2? This is z and this is 2, right. So, z less than 2.00, this probability we want to find out. So, if you look at any book on statistics, you will find a standardized normal table along with other tables which we have seen in previous sessions, like binomial table, Poisson table. So, look at z table. So, this how z table looks like. Here is just a part of that z table. So, on in this column, if you look at z is equal to 0, 0.0, 0.1 and 2 and 3, so and so on, right, 3.1, 3.2 and so on. Similarly, here these are the decimal values. So, let us say if you want to know what is the value of z or what is the area under curve when z is equal to 2.0, right. So, this is 2 and this 0.00. So, this area under curve is 0.9972. So, how it would look like if I draw a curve. Let us look at, let me draw a curve wherein this is, so this is your distribution and this is your z is equal to 0 here, z is equal to 2 here, right, this is 2. Now, we want to know this area and which is 0.9772. So, this area is 0.9772 from minus infinity. So, this minus infinity and this plus infinity, right. Now, let us look at z table, how it looks like. So, this is standard normal probability for positive z score. So, let us say z is equal to 2. So, z is equal to 2, right, here it is, and probabilities are 0.9972. So, what would be the area under curve when z is equal to, let us say 3.05. Okay. So, 3.05 is where, first of all look at 3, right. So, this is 3.00 and then you need, this is 0.05, 0.05 is here, right. So, if you look at here, this is this. So, this is the value 0.9980. 0.9980. So, you can calculate area under the curve from minus infinity to z value. Now, let us say, so this is, let us say at z the area under curve is 0.9972. What is the area under curve when z is equal to minus 2? Look at this, minus 2 is somewhere here, right. It's this is the area under curve when z is equal to minus 2, it is 0.0228. So, there is no need to remember it, you just subtract 1 minus 0.9772, you will get 0.0228. So, if you know the value of z, if you know the value of z, you can easily calculate probabilities, and if it is negative value, then you just subtract that probability from 1, you will get the negative value of z. So, this is how you should read z tables. So, this is one of the z tables. You can have a different type of z table, but you will get the same information. So, in this type of z table, you have got area under the curve from 0 to z value, not from minus infinity to some z value, right. So, it gives you only probabilities from 0 to either some positive direction or negative direction of z value, right. So, let us say what is the value of z when, what is the area under the curve when z is equal to 2, right. So, this is, so z is equal to 2 is here, right, and area under the curve is 0.4772, but in earlier case it was 0.9772. How come? Why there is a difference here? Because here we are calculating z value from 0 to 2. In previous slide we had area from minus infinity to 2, and we also know that the 50% area is this, is not it, or this is 0.5, the remaining is 0.5. So, you just add 0.5 in 0.4772. So, you will get 0.9772, which is the same answer which was there in previous table. So, either you use this table or the other one table, it is one and the same thing, but you should know whether the area under the curve is from mean or from minus infinity. So, this is how you just add this area which is 0.5 and this area which is 0.4772. So, it becomes 0.9772. Let us look at general procedure for finding normal probabilities. Let us say if you want to find out probability between A and B value when a variable is normally distributed having some mean and some standard deviation. So, first of all you should draw the normal curve by taking x into account, then convert x value into z value by using that formula and use standardized normal table to know the area under the curve. So, we will look at how to find out probabilities between A and B in next session. For the time being, let me sign off. Thank you very much.